Morning. Lecture 24. And I think we have an exam on Wednesday, so I'm happy to answer questions, talk about problems on the review sheet, whatever you prefer.
Good morning, Professor.
Morning.
Could you start by like showing us how to do 10?
I'm sorry, could you speak a little louder, please?
Can you start by showing us how to do number 10 and the section 2?
Okay. Just 1 second.
Thank you.
Section 2. You mean section 3.2?
No, I'm talking about the review, Professor. And
Oh, okay. Just 1 second. Let me find that.
again, no problem.
Professor.
Yes. Yeah, go ahead.
Our final will be on December 13th, right?
I have to double check the final exam schedule, but whatever it is on the Lehman exam schedule is when it is.
Okay, thank you.
Sorry, you said December 13th? December
Yes.
13th is the last day of class. It's not the final exam.
I'm sorry, thank you.
Okay. Problem 10, is that the one you're asking about?
Yeah, from the section of the problems. Yeah.
Okay, so review sheet, section 2, number 10 is we have just two polynomials. F of x is 17x to the 5th plus 3x to the 4th plus 2x plus 9, and g of x is x cubed plus 2x minus 1. We just want to divide one by the other first. So if you divide g of x into q of x, that's just long division. So this goes into 17x to the 5th plus 3x to the 4th plus 2x plus 9. So x cubed into 17x to the 5th goes 17x squared times, and you get 17x to the 5th plus 17 times 2 is 34x cubed minus 17x squared. So when you subtract, you get 3x to the 4th minus 34x cubed plus 17x squared plus 2x plus 9. When you divide x cubed into this goes 3x times. You get 3x to the 4th minus 6x squared minus 3x. When you subtract, you get minus 34x cubed plus 23x squared plus 5x plus 9. X cubed goes into this, minus 34. You get minus 34x cubed minus 68x squared plus 34. When you subtract, you get 91x squared plus 5x minus 25. So if I did the algebra correctly, I mean, you have to double check, but in any case, the quotient when you divide is 17x squared plus 3x minus 34. And the remainder is 91x squared plus 5x minus 25. But you always have to go back and double check. Okay. All right. Any questions about that?
No, that part is clear. Thank you.
Okay. Now, what about when you want to do this in the ring Z mod 7Z? So I can do it in two ways. So what we've just shown is that over the integers, the polynomial 17x to the 5th plus 3x to the 4th plus 2x plus 9 is equal to x cubed plus 2x minus 1 times, what was the quotient? 17x squared plus 3x minus 34. And the remainder was 91x squared plus 5x minus 24 minus 25. So mod 9 17x to the 5th plus 3x to the 4th plus 2x plus 9. Sorry, mod 7. I mean, this is the same as 3x to the 5th plus 3x to the 4th plus 2x plus 2. Mod 7. The quotient 17x squared plus 3x minus 34 is congruent to 3x squared plus 3x minus 34 is the same as 1 mod 7. And the remainder 91x squared plus 5x minus 25. Well, this is the same. 91 is 0 mod x squared. So this is the same as 5x plus 3 mod 7. So mod 7, this is the quotient, and this is the remainder. You could also, if you like doing arithmetic mod 7, we're dividing x cubed plus 2x minus 1. Let me write everything positive. It's the same as plus 6. We're dividing it into 3x to the 5th plus 3x to the 4th plus 2x plus 2 in the field with 7 elements, Z mod 7Z. So x cubed into this goes 3x squared times. You get 3x to the 5th plus 6x cubed plus 18, which is the same as 4x squared. When you subtract, you get 3x to the 4th minus 6x cubed minus 4x squared plus 2x minus 2. X cubed into 3x to the 4th goes 3x times. So you get 3x to the 4th plus 6x squared plus 18x, which is the same as 4. So you subtract, you get minus 6, which is the same as plus 1, x cubed. Minus 4 minus 6 is minus 10, which is mod 7 is the same as 4, right? Because let's see, minus 6 minus 10 is the same as minus 4. 2 plus 4 is 6, minus 2. X cubed goes into x cubed once. So you get x cubed plus 2x squared. Oops, sorry. X cubed plus 2x plus 6. So this remainder is 4x squared plus 4x minus 8, which is the same as minus 1, which is the same as, sorry, minus 2, minus 8, minus 1, plus 6.
Professor.
Yeah, oh, sorry. I'm
Isn't it-
doing, yeah,
Isn't
go
it
ahead.
Doesn't minus 6x cubed come straight down?
Yes, but minus 6 mod 7 is the same as plus
Oh,
1.
okay, understood.
So this part is right. I just have to check my remainder. But sorry, so again, check. But I don't want to spend the time now doing the arithmetic. But this is the method. That's the important thing. It's just doing high school algebra, but in a more sophisticated setting of a finite field. The first part is just long division of polynomials, which is pre-calculus. And then the observation is that in the field of the integers mod 7, z mod 7z, in that field, you can also do arithmetic, either by taking your expression in z and just reducing everything mod 7. Or just by doing long division, but doing it in the field z mod 7z. That's what it is.
Professor, can you do 9?
Sorry,
Can you do 9?
in section 2?
Yeah,
Okay.
at least one to refresh.
So section 2, number 9. So these are 4 separate problems. Solve x squared plus 4x plus 2 congruent to 0 mod 7. So mod 7, that's a 7's a small number. You could just try plugging in x equals 0, 1, 2, 3, 4, 5, and 6 and see what you get. Or if you want to do it algebraically, you can complete the square. This is the same as x squared plus 4x plus 4 congruent to 2 mod 7. I just added 2 to both sides. So this is just x plus 2 squared congruent to 2 mod 7. So is 2 a square mod 7? So if you take the Legendre symbol, 2 over 7, this is equal to 1 because z is congruent to minus 1 mod 8. So this does have a solution. So you know it has a solution. What are the, suppose you want to solve, so just for a second, let y equal x plus 2. So you're solving y squared congruent to 2 mod 7. And you know that 3 squared is congruent to 2 mod 7 because 9 minus 2 is 7. And 4 squared is congruent to 2 mod 7, because 16 minus 2 is 14. So you can let y, which is x plus 2, be equal to 3 or 4, which means x is equal to 1. If x plus 2 is 3, x is 1. If x plus 2 is 4, x is 2. So the solutions are 1 and 2. So this was the first. In the second, x squared plus 4x plus 2 congruent to 0 mod 5. Again, you just have to plug in 0, 1, 2, 3, or 4 and see if there's a solution. Or you can say this is exactly the same as the equation x plus 2 squared congruent to 2 mod 5. But if you take the prime p equal 5, the Legendre symbol 2 over 5 is minus 1, because 5 is congruent to minus 3 mod 8. So you don't even have to check. There's no solution because 2 is not a square mod 5. Right. Questions about that? And a similar technique has to work for the next two problems. Obviously, there's a mistake because I repeated it. I probably should have meant 13 instead of 11. Or 17 maybe. So in the third case, we want to solve x squared plus 9x plus 7 congruent to 0 mod 11. Well, I mean, it's always nice to complete the square. So this is the same as x squared. See, 9 is the same as minus 2 minus 2x congruent to minus 7 mod 11. And if I add 1, which I can do, then this is x minus 1 squared congruent to minus 6 or 5 mod 11. So I need to know, is 5 a square mod 11? So what is 5 over 11? This is the Legendre symbol. So 5 is congruent to 1 mod 4. So by the quadratic reciprocity, this is the same as 11 over 5. 11 is 1 mod 5, so that's the same as 1 over 5, and 1 is a square. So this does have a solution, right? And then we have to find it, I guess. So, and I guess you just have to try. Let's see, 1 doesn't work, 0 doesn't work, 1 doesn't work, 2 doesn't work, 3 doesn't work, 4 doesn't work, 5 does work. If you let x equal 5, 5 minus 1 squared is 4 squared is 16, is congruent to 5 mod 11. And so x minus 1 equals 5 is a solution, and plus or minus 5 will be, minus 5 will also be a solution. If x minus 1 equals minus 5, x is minus 4, or if you like, 7 mod 11. So if you take x equals 7, 7 minus 1 squared is 6 squared is 36. Let's see, is that right? Something's not right here. When x minus 1 is 5, sorry. Yeah, when x minus 1 is 4, plus or minus 4. So when x is 4, when x minus 1 is 4, x is 5. When x minus 1 is minus 4, x is minus 3, which is the same as 8. So 8 minus 1 squared is 7 squared is 49, is congruent to 5 mod 11, because 49 minus 5 is 44, which is 4 times 11. So the solutions of this congruence are x congruent to 5 or 8 mod 11.
Thank you, Professor.
Okay.
Does anyone else have a question, or I can continue asking because no one wants to say anything?
Professor, thank you. Can you go over number 7, please?
In
Session
section
2.
2?
Yes.
Sure. So this is computing some Legendre symbols. So we want to compute first 19 over 3. So 19 is congruent to 3 mod 4. So when both the prime and the numerator and the denominator are congruent to 3 mod 4, you can flip this over, but it changes sign. It's minus 19 over 3. And 19,
Professor,
what?
quick question. When you say
Sorry,
flip
oops.
over is 3 over 19, right?
Yeah, thank you.
I have another question. If you have 19
Oh, I'm
over-
sorry. What I said is correct, but it's silly. So for 19 over 3, all you have to know, you can always reduce
That's one.
modulo the denominator. So 19 is congruent to 1 mod 3. So 19 over 3 is the same as 1 over 3, and 1 over 3 is 1.
Oh, yeah, that's what I
Okay.
was looking.
Right? Any questions about that?
Sorry,
One of the
Professor.
basic properties of the Legendre symbol is that if A is congruent to B mod P, then A over P is the same as B over P for the Legendre symbols. So 19 is congruent to 1 mod 3. So 19 over 3 is the same as 1 over 3, which is 1.
Professor, when I was looking at it, can you just let me know if I just went down the wrong path? I was looking at A with the P minus 1 divided by 2 mod P, and then is that just the wrong way to do it?
Well, so it is true that A over P is congruent to minus 1. It's congruent to A to the P minus 1 over 2 mod P. But if you take 19, yeah, so in this case, yeah, so this would say is congruent to 19, so P is equal to 3, is congruent to 19. All right, sorry. So 19 over 3 is congruent to 19 to the 3 minus 1 over 2, which is just 19 mod 3. and 19 is congruent to 1 mod 3. So this gives you the correct answer. But in most cases, if you try to use this congruence, you'll get some very big number here, which is hard to calculate. And if you go through all the work, you will get the answer, but it's much easier to use quadratic reciprocity or to use just this simple property. But this is okay. This gives you the right answer. There's no problem with that.
Can you do another example of the same number, please?
Sure. Let's look at minus 13 over 17. So this is the same as minus 1 times 13 over 17. Again, another property of the Legendre symbol is that AB over P equals A over P times B over P. So this is minus 1 over 17 times 13 over 17. Minus 1 over 17 is plus 1. We know that minus 1 over P is equal to 1 if P is congruent to 1 mod 4, and minus 1 if P is congruent to 3 mod 4. So 17 is the 1 mod 4. So minus 1 over 17 is plus 1. This is just the same as 13 over 17. Now these are odd primes, and both of them, in fact, are congruent to 1 mod 4. So I can flip this over by quadratic reciprocity. That's 17 over 13. By quadratic reciprocity. And 17 is congruent to 4 mod 13. So this is 4 over 13. 17 is congruent to 4 mod 13. And 4 is a square, so this is 1.
Professor, I have a question.
Yes.
When is the case where you use quadratic reciprocity and you have to put a negative in the front?
So quadratic reciprocity says that P over Q equals Q over P. You don't change the sign. If P is congruent to 1 mod 4 or Q is congruent to 1 mod 4 or both, and P over Q is minus Q over P if P and Q are both congruent to 3 mod 4.
Can you pull the paper a little bit up? So, okay, got it. Thank you, Professor. Okay.
Right? This is quadratic reciprocity.
Professor,
Yeah.
can you solve another one using Gauss lemma?
Well, I'm not using Gauss's lemma for any of these.
Okay.
I mean, there were some homework problems involving Gauss's lemma, but let me do one more of these just so, because this is really important to learn how to use the quadratic reciprocity symbol. So we had 30 over 17. So again, we factor 30 as 2 times 3 times 5 over 17. So that's 2 over 17, 3 over 17, 5 over 17. So we have to compute these three symbols separately. 2 over 17 is 1 because 17 is congruent to 1 mod 8. We know exactly when 2 is a quadratic residue modulo a prime, when the prime is congruent to plus or minus 1 mod 8. So this is plus 1. 3 over 17. 17 is congruent to 1 mod 4. 3 is not, but you only need one of the two in order to be able to flip this. So this is 17 over 3. And 17 is congruent to 2 mod 3. So this is 2 over 3. And 2 is not a quadratic residue mod 3. 3 is not plus or minus 1 mod 8. So this is minus 1. And what about 5 over 17? Again, 5 and 17, they're both congruent to 1 mod 4. So this is 17 over 5. 17 is congruent to 2 over 5. 2 is not a quadratic residue mod 5. 5 is not congruent to plus or minus 1 mod 8. So this is minus 1. So what we get here is 1 plus 1 times minus 1 times minus 1, which is 1. So 30 is a quadratic residue mod 17. We could also have done, so that's one way to do this problem, right? Second method, even easier. 30 is congruent to 13 mod 17. So 30 over 17 is the same as 13 over 17. These are primes congruent to 1 mod 4. So this is 17 over 13. 17 is 4 mod 13. 4 is a square, so this is 1. So one method, a little bit of work, get a plus 1. Second method, less work, but you still get the right answer. What about, is 56 a quadratic residue mod 61? 56 is 8 times 7. 2 cubed times 7 over 61. So that's like 2 over 61 cubed times 7 over 61. 61 is congruent to minus 3 mod 8. So 2 over 61 is the minus 1. So this is minus 1 cubed. 7 over 61. 61 is 1 mod 4. So you can flip this. This is 61 over 7. 61 mod 7 is 5, right? 61 minus 5 is 56, is divisible by 7. So this is 5 over 7. Right? So here I'm using quadratic reciprocity. 5 over 7, 5 is 1 mod 7. So I can also flip this. I can use quadratic reciprocity a second time. This is 7 over 5. 7 is the same as 2 mod 5. 2 over 5 is minus 1. So what we have here is minus 1 cubed times minus 1, which is plus 1. So 56 is a quadratic residue mod 61. This method doesn't tell us how to find the solution. So we know that there exists an integer x such that x squared is congruent to 56 mod 61. There exists, but this doesn't tell us how to find it. Any
Professor.
questions about these?
Professor,
Yeah,
in this example, would the arithmetic be too hard for you to go through it to find the solution?
yes.
Okay,
I mean, you could be lucky, you could find a small number quickly that's a solution. But if not, then you know, you have to check the numbers 1 through 30 because for X, because from 31 to 60, each of those is just a negative of one of these.
understood. Gotcha. Thank you.
So just 1 second, please. Okay. Yeah. Other questions?
Professor, can you go over proof number 3, please?
Sure. So G is a finite cyclic group. Of order n, with identity element we'll denote by the letter E. Prove that if X is in G, then X to the D is the identity for some divisor D of n. So the important thing is that G is finite. So if we start looking at the sequence of elements, x squared, x cubed, x to the 4th, and so forth, even when we get up to, let's say we take n of them, x to the n plus 1, these cannot all be distinct. Why are they not all distinct? Because the group only has n elements. So if I write down any n plus 1 elements in the group, here are n plus 1 elements, they can't be different. There are too many of them. So there exist integers, positive integers, I less than j, with x to the I equal x to the j, right? Two of these have to be equal, right? Okay. So that's an important method of reasoning. We have a set with n elements. If I write down n plus 1 elements, they can't all be different. They all belong to the set. So two of these are the same. There's an I and a j with x to the I equal to x to the j, and I is less than j, right? G is a group. So x has an inverse. I'll write it as x to the minus 1. So if I take x to the I equals x to the j, if I multiply by x inverse to the I, which is x to the minus I, that's x to the j times x to the minus I. X to the I times x to the minus I is e, and this is x to the j minus I. So j minus I is some positive integer. So what this says is, in a finite group, for every x, there exists some k. In this case, j minus I is equal to k. Some k greater than or equal to 1, with x to the k equal to the identity. Now, so what this says is that some positive power of x is the identity. The order of an element is the smallest, because there can be lots of k's that satisfy this equation, is the smallest positive integer k, such that x to the k is the identity. Right? And if k is the order, must show k divides n. Right? So let's see. So we have the order of G is n, and x to the k equals e. K is the smallest positive integer with this property. So divide n by k. So this is just the division algorithm. N is kq plus a remainder, where the remainder is between 0 and k minus 1. So x to the n is x to the kq plus r. This is x to the kq times x to the r. This is x to the k to the q times x to the r. X to the k is the identity. The identity to a power is the identity. This is x to the r. And yeah. So if x to the n is the identity, then x to the r is the identity, but r is smaller than k, so r equals 0. So n equals kq, and k divides n. So this proof depends on the fact that if you have a group of order n, the order of every element x to the n is always the identity. So so I had already proved this, so I use this, but let me prove this the way I proved it in the lectures and in the book. So you have a group G, finite group. You take a subgroup H. We look at the left cosets AH. So G mod H, this was the set of left cosets. And we proved that the order of the subgroup H divides the order of the group. Right? So this was a major theorem in the text. If you have a finite group, the order of a subgroup divides the order of a group. So if you let X be in the group and I write X with brackets around it, the set of all powers of X, this is what is called the cyclic subgroup generated by X. And this group, this subgroup, cyclic subgroup generated by X, has order equal to the order of X. That is, the number of elements in this set is exactly the smallest positive power of X that equals the identity. And since the order of a subgroup divides the order of a group, the order of every element in the group divides the order of the group. So So this is what I had proved in the text, that the order of a subgroup divides the order of a group. If you take an element, you look at the cyclic subgroup it generates, the number of elements, that the order of the subgroup is the order of the element, and that's the divisor of the group. If you want a completely different proof that doesn't use this kind of machinery, let's try the following. So suppose G is a finite group. Of order n. So let's say it consists of the elements A1, A2, A3, up to A sub n. Let X be in G. So if X times AI equals X times AJ, right? AI, AJ are two elements of the group, then AI equals AJ. Or conversely, if I is different from J, then XAI is different from XAJ. So consider the following n elements of G. XA1, XA2, XA3, up to XAN. So these are distinct. But there are only n elements in G. So these n elements just have to be some permutation of these n elements. So this is just equal to A1, A2, up to A sub n. But of course, what you have here is you have X to the n, A1, A2, up to A sub n. So divide by A1, A2, up to A sub n, and you get X to the n is the identity. So this is a very simple proof that the order, that if X is an element of group of order n, X to the n is equal to the identity. And if X has order K, then K has to divide n by the proof I gave a few minutes ago. So in any case, this is a problem that gives a lot to think about. Right. Other things I should go over?
Professor, problem 5, please.
In which section?
And the review exam.
Sorry?
And the review in the same paper.
No, but there are 3 sections in the review. There are 3
Oh,
problem
the
parts.
problems. There are
Problem-
2.
Oh, okay, very good.
Thank you.
So problem 5 is just to compute the Legendre symbol. So we know 2 over P is 1 if P is congruent to plus or minus 1 mod 8, and minus 1 if P is congruent to plus or minus 3 mod 8, which is the same as minus 1 raised to the power P squared minus 1 over 8. So to compute the Legendre symbol, 2 over 3, 3 is 3 mod 8 is minus 1. 2 over 7, 7 is minus 1 mod 8, so that's plus 1. 2 over 11, 11 is 3 mod 8, so that's minus 1. 2 over 13, 13 is 1 mod 8, that's plus 1. 2 over 17, 17 is plus 1 mod 8 also. Sorry, 13 mod 8 is 5, so this is minus 1. 17 is 16 plus 1, this is 1 mod 8, so this is plus 1. So we just use this rule, this formula that tells us exactly for what primes 2 is a quadratic residue.
Professor,
Yeah,
why did you say the 5 mod A will be minus 1?
sorry?
So for the Legendre symbol 2 over 13, you say that 5 mod 8 will be minus 1. Why?
No. 13 is congruent to minus 3 mod 8. If a prime P is
Okay.
congruent to minus 3 mod 8, 2 over that prime is minus 1.
Yeah, I got it. Thank you. Thank you, Professor.
Sure.
Professor,
Yes.
can you do from the proof section number 6?
So we want to prove the theorem that said that if P is congruent to 1 mod 4, then -1 is a quadratic residue mod P. And so let's follow the hint. The equation x squared minus 1 has exactly 2 solutions, right? So x squared congruent to 1 mod P. P is always an odd prime. Has what solutions? X congruent to either plus or minus 1 mod P. So a polynomial of degree D has at most D solutions mod P. This is solving a polynomial of degree 2. There are at most 2 solutions. And in fact, there are exactly 2, plus 1 and minus 1. That P be a prime of the form 4k plus 1. And let G be a primitive root mod P. That means that if any A is not congruent to 0 mod P, then A is congruent to G to the K mod P for some K. The powers of this primitive root give every congruence class mod P. So and G has order P minus 1 mod P, right? We know that every element raised to the power P minus 1 is congruent to 1 mod P. And if for a primitive root, the smallest order is P minus 1. So so if A is congruent to 0 mod P, I shouldn't use K. I'm writing P as 4K plus 1. So every congruence class is some power of G mod P. But so P is 4K plus 1. So P minus 1 is 4K. P minus 1 over 2 is 4K over 2 is 2K. So G to the power 2K is not congruent to 1 mod P, because G has order P minus 1, which is 4K. The smallest power of G, which is congruent to 1 mod P, is the power P minus 1, or 4K. So G to the 2K is not congruent to 1 mod P. On the other hand, G to the 2K squared is G to the 4K is congruent to 1 mod P. And what are the square roots of 1 mod P? G to the 2K has to be congruent to plus or minus 1 mod P. And so G to the 2K is congruent to minus 1 mod P. So let me repeat the argument, because it really is not such a complicated thing. So you take G, a primitive root mod of prime P, which is of the form 4K plus 1. So we know that G to the 2K is not congruent to 1 mod P, but G to the 2K squared, which is G to the 4K, is congruent to 1 mod P, right? Because 4K is P minus 1. G to the P minus 1 is congruent to 1 mod P. But X squared congruent to 1 mod P has only two solutions. X congruent to 1 mod P and X congruent to minus 1 mod P. And G to the 2K, when you square it, is 1. So G to the 2K is either 1 or minus 1 mod P. And it's not 1. So G to the 2K, which is G to the K squared, is congruent to minus 1 mod P. So minus 1 is a square. So following the hint, that's the proof.
Could you do 5, Professor? Hello, Professor.
Yeah.
Could you do 5 from the proofs also?
Sorry?
Could you do 5 from the proofs also?
Yeah.
Thanks.
So there's a very close connection between number theory and algebra. So many of the proofs in group theory are really just proofs in number theorem. And proof number 5 is another of this sort. Suppose G is a finite cyclic group of order n, that A be a generator of G. So this means G consists of the elements E, A squared, A cubed, up to A to the n minus 1. And A has order n. A to the n is equal to E. Let X be in G. So X equals A to the K for some K. Let D be the greatest common divisor of K and N. So if we take X to the power n over d, which is an integer, because d divides n. This is a to the k to the power n over d. This is a to the kn over d. D also divides k. This is a to the n times the integer k over d. That's like a to the n to the k over d. And a to the n is the identity. So x to the n over d is equal to the identity. Suppose, that doesn't mean that n over d is the order of x, but we know that x to this power is the identity. Suppose we let, I don't know, x have order m. So then x to the m, which is a to the k to the m, equals the identity. So if a to the km equals e, then n divides k times m. D divides n and k, so n over d divides k over d times m. But n over d and k over d, these are relatively prime integers. Because if you take k and n and you divide by their greatest common divisor, d, then k over d and n over d are relatively prime. So if n over d divides this product, and n over d is relatively prime to k over d, so by Euclid's lemma, from the very beginning of the course, n over d divides m. So if x has order m and x to the n over d, so x to the n over d equal 1 implies m also divides n over d. Because if an element to a power is 1, that power is divisible by the order. So m divides n over d, and n over d divides m. You put these two together and you get m equals n over d. So that's the proof. And Euclid's lemma is central to this, and this is really just another bit of number theory.
Professor,
Yeah,
could you do proof number 4 as well, please?
that's just computing the Legendre symbol. So we know that -1 over p is equal to 1 if p is congruent to 1 mod 4, and -1 if p is congruent to 3 mod 4.
No, Professor, proof number 4.
This is problem number 4.
Proof,
Sorry?
proof.
Proof. Oh, sorry.
Yes, thank you.
Okay. No problem. Proof number 4. So G is just the congruence class is mod M. And we can write M as D times D prime. So D prime divides M, and M over D prime equals D. Okay? So consider the congruence class. D prime plus MZ. So that's one congruence class in Z mod MZ. The order of this congruence class is the smallest integer. Let's call it K, such that K times D prime plus MZ is 0. Equals MZ. Right? That is, K is the smallest integer such that, I mean, this is KD prime plus MZ, such that KD prime is congruent to 0 mod M. So KD prime is some multiple of M, QM, if and only if K is Q M over D prime, just dividing by D prime, which is Q times D, because M over D prime is D. So the smallest integer such that K is a multiple of D is D. D times D prime is M. So that's the proof. D prime plus MZ has order D if M is D times D prime. Any questions about this?
No, Professor, thank you.
Yeah. Someone asked about number 7, but I had started by doing some of those. Other problems?
It-
Yeah, go ahead.
Professor, for the definition, so For example, number one, right? So when you say G is a primitive root modulo A prime P, it's like, for example, that what you mean is like how many primitive roots 6 when P is prime or something like that, because there are many definitions using this. I don't know
Sorry, so which question are you asking about?
about definitions. Part one.
Oh, okay, so G is a primitive root modulo P if for every A that's relatively prime to P, there exists a K such that A is congruent to G to the K mod P. Equivalently, if you take Z mod PZ star, this is just the non-zero congruence classes mod P, and this is just all the powers, all the cosets, G to the K plus G to the K plus P to the Z. K goes from 0, 1, 2 up to P minus 2. So, but every non-zero congruence class mod P, every integer not divisible by P is congruent to some power of G. So for example, if you take P equal to 5 and G equal to 2, what are the non-zero numbers mod 5? 1, 2, 3, and 4. So 1 is congruent to 2 to the 0 mod 5. 2 is congruent to 2 to the first power mod 5. 2 squared is congruent to 4 mod 5. 2 cubed is congruent to 8 mod 5. So every non-zero number mod 5, 1, 2, 3, and 4 is a power of 2. So 2 is a primitive root mod 5. If you take P equal to 7 and G equal 3, what are the powers of 3? 3 to the 0 is congruent to 1 mod 7. 3 to the first power is congruent to 3 mod 7. 3 squared is 9, is 2 mod 7. 3 cubed is 27, is 6 mod 7. 3 to the fourth is 81, is 4 mod 7. 3 to the fifth is 243, is 5 mod 7. Or if you want to write this, just rearrange this. 1 is congruent to 3 to the 0 mod 7. See, 2, 3, 4, 5, and 6. 2 is congruent to 3 squared. 3 is congruent to 3 to the first. 4 is congruent to 3 to the fourth. 5 is congruent to 3 to the fifth. 6 is congruent to 3 cubed. So every non-zero congruence class mod 7 is a power of 3. So for example, mod 5, G equal 2 is a primitive root. For P equals 7, G equal 3 is a primitive root.
Thank you, Professor. I just was confused because there are many definitions, also theorem that is the same statement for number one and also all of them. So I just wanted to see like a concrete definition about this.
Right. So there are many equivalent definitions. And if I were to ask you for a definition, any definition that's correct would be okay.
Okay, good to know. Thank you.
Sure.
Professor, are you offering office hours to them tomorrow?
So I was going to have 2 office hours tomorrow, 1 in the morning and 1 in the evening around 7. I can also have an office hour tonight. If anyone is interested, just send me an email. And if I get even 1 email saying someone will show up, I'll have an office hour tonight at 7 o'clock. But I'm going to have office hours tomorrow, I think at 9 o'clock in the morning, and again at 7 in the evening.
Okay, thank you.
Question?
Professor,
Yeah,
can you do number 3, problem number 3?
sure. So for problem 3, take p equals 7 and g equal to 5 is a primitive root. So what are the powers of 5? 5 to the 0 is congruent to 1, mod 7. 5 to the first power is congruent to 5. 5 squared is 25, which is the same as 4 mod 7. 5 cubed is 5 times 5 squared, which is 4 times 5 or 20, which is the same as 6 mod 7. 5 to the 4th is 5 cubed times 5, which is 6 times 5, which is 30, which is 2 mod 7. 5 to the 5th is 5 to the 4th times 5, which is 2 times 5, which is 10, which is 3 mod 7. And 5 to the 6th is 5 times 5 to the 5th. That's 5 times 3, which is 15, which is back to 1 mod 7. So, so if we look at 1, 2, 3, 4, 5, 6 mod 7, 1 is congruent to 5 to the 0. 2 is congruent to 5 to the 4th, mod 7. 3 is congruent to 5 to the 5th, mod 7. 4 is congruent to 5 square mod 7. 5 is congruent to 5 to the first power mod 7, and 6 is congruent to 5 cubed mod 7. So for the numbers 1, 2, 3, 4, 5, 6, what call that number A? What is the index of A with respect to the primitive root 5? That means what power of 5 gives you each of these numbers? Well, 5 to the 0 is 1, 5 to the 4 is 2, 5 to the 5th is 3, 5 squared is 4, 5 to the 1st is 5, and 5 to the 3 is 6. So the index of 1 is 0, the index of 2 is 4, the index of 3 is 5, and so forth. Right, so this table gives me this table, and this table gives me this table.
So Professor, for A equal to 1, right? So since the lower power will 5 to the 0 equals to 1, so in the index of 1, it just 0, it cannot be 6.
Correct.
You have to be the small. Okay.
Yeah. Yeah. You want the smallest non-negative, the smallest non-negative integer.
Okay, got it.
Other questions?
Can you please solve problem 4, please?
Well, but for problem 4, it's minus 1 over p. So we know this is 1 if p is congruent to 1 mod 4, and minus 1 if p is congruent to 3 mod 4. So if you take the prime p equal 3, minus 1 over 3 is minus 1 because of this. If you take the prime 13, minus 1 over 13 is plus 1 because of this. You just look at the congruence class of the prime mod 4. All right. Okay. So if there are more questions, again, I'll be online tomorrow, let's say at 9 o'clock in the morning and at 7 o'clock in the evening.
I'm having problems completing your request. Please try again later. If you continue to have issues, please contact support.
Ooh, I don't know what that is. Okay. Okay, all. That's it for now. Let's see, I guess we have an exam on Wednesday morning. And again, if there are questions, I'm available several times tomorrow.
Thank you, Professor.
Okay, bye all.
Thank you, Professor. Have a good day.
Thank you.